Hello, I'm Dr. Steck. Welcome to CS797 Part 2 of this lecture series. Today we're going to review a bit about artificial neurons. We're going to look at some logic gates and perceptrons. And we're going to look at the perceptron training rule. All right, so let's start off. This is a review of what Dr. Brooking went through. Remember, the biological neuron has a cell body and an output called an axon, and some inputs called dendrites. And these dendrites connect to another neuron output with something called a synapse. And the body here, this is called the soma, or the cell body. So the four major parts are the dendrites, the axon, the soma, and the synapse. And then an artificial neuron is modeled after the just really basic behavior of the biological neuron. The cell body is represented by a summation and an activation function. The output is modeled after the axon, and then the artificial neuron has inputs. I'm just going to draw three, but there can be many of these. And the input values are x1, x2, and x sub n. And these are multiplied by weights. And then those are added up with the summation, and then the activation function is applied to the summation to create the output. According to the formula, we do this in stages. We call something U is the net input, and it's equal to the sum of all the weighted inputs so that's the net input, and then the output is that activation function F applied to U. So that's how an artificial neuron works. And the artificial neuron, again, the different pieces and parts have a correspondence. The dendrites are the inputs. The synapses are corresponding to the weights. The soma, or the cell body, corresponds to the summation and the activation, and the axon is the output. the activation functions need to be defined. Some common useful activation functions are, number one is linear, and that just means that we take the input and we multiply by some constant k. And if you look at a plot of this, k is the slope that multiplies u. Usually the slope is 1, but not always. Another activation function is called the hard threshold. And its formula looks like this. It's 0 when the input is below some defined threshold. And then once the input gets above the threshold, it outputs a 1. Plot of that looks like this. It's 0 up until you hit that threshold, and then it jumps up to 1. Another useful one is called the sigmoid. And it's a soft threshold. And it looks like this. Its plot looks like this. It goes from 0 to 1 as u goes from negative infinity to positive infinity. And it mimics the hard threshold, but it's a softer rise up from 0 to 1. The sigmoid only goes from 0 to 1, and sometimes we want neurons to be able to output negative numbers. And so people sometimes use what's called the tan-h. And that's just the tan-h function of the net input to the neuron. And its plot looks just like the sigmoid, only it goes from -1 to 1. The last one, not by any means an exhaustive list, but the last one I'm going to talk about is called the radial basis function. And it looks like this. It's the exponent of the distance between the input and a value A that marks the center of a Gaussian hump. So this looks like this. It's a bump function. And the center of the bump is that value A. This neuron is designed to mimic how certain regions of the brain will respond to certain inputs. And so you can see that this responds to a region of input, a narrow region of input space in the U-axis. All right, the next topic we're going to talk about is some simple logic gate networks. So our network, our logic gate, is a 2-input, 1-output logic gate. We're going to list the values. These are binary zeros and ones. And so this OR gate, if a 0 and a 0 go in, then neither 1 nor 2 inputs are high, so it's a 0. If either one of the inputs is a 1, then we get a 1 out, and if both are a 1, we get a 1 out as well. So this is the OR applied to the 2 inputs. So let's look at a neural network that does this logic gate. So let's leave the data there. Draw 2 input neurons. And all these do is copy the input to the output. And they're linear. So they have the linear activation with a slope of 1, so what goes in comes out. And let's add an output neuron. And it's going to be a hard threshold. And the threshold is going to be set to 0.5. So if the input's greater than or equal to 0.5, it's going to output a 1. And then we're going to connect the input neurons to that single output neuron with weights. We're going to start talking about a numbering strategy of how to number neurons and weights. And so call that neuron number 1, and this number 2, and this number 3. And a weight is going to be designated as going from 1 to 3 with this designation. So this weight goes from 1 to neuron number 3. And here, this would be called W3, 2, because it goes from 2 to 3. And its weight value is going to be +1. So remember how a neuron works. It takes its input, sums up all the inputs, applies the activation function, and then spits out the output. So let's process this up here with our data. So notice that the OR column here indicates the correct value. Let's see what we actually get. So neuron number 1, its output, it just matches the input. And so we're going to call its output x1 and x2. So those are the outputs from the neurons. And they're going to copy the input. Now for the third neuron, we need to do some calculations. It's going to take the 2 inputs coming into it and add them up to create the net input U3. Let's see if I can make that 3 better. There we go. And then we're going to apply the activation function to calculate x3. So let's look at the neural net. A 0 goes in here, and a 0 goes in here. And 0 times 1 plus 0 times 1 gives us the net input to neuron number 3. Now we look at that and we say that's less than the threshold of 0.5, and so that neuron does not fire, it outputs a 0, because we're applying the threshold activation function here. Let's do the next input pair. So we're going to put in a 0 and a 1. So neuron 1 outputs a 0, neuron 2 outputs a 1. And then we take 0 times 1 plus 1 times 1 and add those together, and we get a net input of 1, and that's greater than the activation function, and so that neuron fires. Next set, we put a 1 in here and a 0 in here, so we have 1 times 1, 0 times 1, so we get a net input of 1 greater than the threshold, and so the output is 1. You can see how this works pretty easily once you get the hang of it. You put a 1 and a 1 in, so you get 1 times 1 plus 1 times 1, those are the weights, and that gives you a 2 as the net input, and of course that's greater than the threshold, so you get a 1. And so if you notice that all of the outputs are correct. So that works. Now let's say we wanted to try to do a different logic gate. We're going to do this on top of here. If we wanted this network to output a 0 when it's a double 1 input, that would be the exclusive OR. Does this work? Well, no, because when we put in the 1 and the 1, we still get the same values here. We get the 2 here. It's bigger than the threshold, and that doesn't work. Works for the first 3 rows, but for the 4th one it does not. And in fact, it turns out that a network with just an input layer and an output layer cannot represent this function. People tried for years, and in fact, a group of mathematicians proved that this type of network structure cannot do an XOR, a nonlinearly separable problem. So we're going to have to expand the network. What we really need is something that's going to turn off the output for just the 4th set of inputs, but not the other 2. So let's look at the XOR net. So let's draw our network. It's still a 2-input, single output logic gate. I'm going to put an output neuron up here. It's going to have a threshold of 0.5. These are going to be linear with a slope of 1. We still need connections here. We're going to add another neuron here with some connections like this, and that's going to have a threshold of 1.5. And we're going to have a weight here of -2, and we still have +1 and +1 for the weights here. And our numbering scheme is going to be, this is neuron number 1, this is neuron number 2, this is neuron number 3, and this is neuron number 4. Let's see how this works. Notice that we have a negative weight here, and that's going to play into calculating that 3rd or that 4th set of inputs. So let's create another table over here. We're going to put our inputs here, list them. 0, 0 going in. We need to calculate U3, the net input for neuron 3. We have to calculate the output of neuron 3. Then we're going to have to calculate the net input for neuron 4 and the output for neuron 4. All right, so let's process this network. 0 going in, 0 going in. Oh, I forgot to tell you the weights here. We got a 1 here and a 1 here as well. All right, so we get 0 times 1 plus 0 times 1 gives us a net input of 0, less than the threshold of 1.5. So neuron 3 does not fire and outputs a 0. We needed to calculate this in order to calculate X4 and U4 because we have to know the value going along that path. So now U4 is going to be 0 times 1 plus 0 times 1 plus 0 times minus 2. All those zeros add up to 0. It's less than 0.5, so we get 0 coming out. Let's try the other sets of inputs. So we put in a 0 and a 1. The net input for neuron 3 is 0 times 1 plus 1 times 1. So that's going to be a 1, which is still less than that threshold of 0.5, so 3 puts out a 0. Now let's do neuron 4. We get a 0 times 1 plus a 0 times 1. Sorry, plus a 1 times 1, because now we've got our input here is a 1. So 1 times 1, 0 times 1, so that's 1. And so for this, sorry, back up. We're doing neuron number 4 now. All right, so we get 0 times 1 plus 1 times 1. So we get a 1, and then we still have a 0 times the minus 2. So we have a net input of 1 here that's bigger than the threshold, so neuron 4 fires. And this is symmetrical, the network's symmetrical, so the same thing's going to happen here, but let's talk through it. We have a 1 going in here, a 0 here. So for neuron 3, we have 1 times 1 plus 0 times 1, so the net input is 1, which is less than the threshold, so that one does not fire. And then for 4, we add up 1 times 1 plus 0 times 1 plus 0 times minus 2, bigger than the threshold, so that neuron fires. So far, so good. Let's put in the 1, 1. Do neuron number 3. We have 1 times 1 plus 1 times 1 is 2, and that's bigger than the threshold. And so now, for this input, X3 fires. And now let's add up the net input for neuron 4. We have 1 times 1 plus 1 times 1 is 2, plus neuron 3 is putting out a 1, so we have a minus 2. So we get a plus 2, minus 2, so this now is a 0. So that's less than the threshold. And now that neuron does not fire. And notice that that's the role of neuron number 3, is it inhibits the firing of number 4 when we have a double 1 as an input. And so these are all correct now. All right, some terminology. This first set of inputs, the 0, 0, is called a pair. And if we're learning, it's a training pair. when it's coupled with the correct output. So to create the training pair, we want to add in the correct output for the logic gate. So a training pair is a set of inputs coupled with its correct answer, and then we look over here and we see, well, it got the correct answer. Second training pair is this set of inputs coupled with the correct answer. Another training pair is this, and another training pair is this, or training data or data. All right, so that's some terminology. A training pair is some inputs paired with the correct output. And maybe we see that more clearly if we go back up to the previous value. This, with its correct value, is a training pair. This is another training pair. This is another training pair. And then this is the fourth training pair. All right. Another notation is that we've been looking at what are called feed forward nets. Why? Notice that the data goes from the inputs to the output in a forward fashion. There are no connections that go backward. It's possible that we could say, hey, let's take the output from neuron 3 and feed it back into this neuron, or the output from neuron 4 and feed it back into this neuron. Those are called recurrent connections, and on a feed-forward network, you don't use those. And it makes it much more difficult to process the network because you need the answer from neuron 4 to be able to get the output from neuron 3. Also, notice that what we've been doing is we haven't been, each network is tailored to a specific problem. So for the OR problem, we just defined a network. But where did that come from? I wrote it down. For these simple logic gates, it's pretty easy to say, by trial and error and just trying activation functions to get a network that works. Same thing for the XOR. I said we needed that middle neuron, but how did we arrive at that network? Another set of, or another terminology that we need to talk about is that middle neuron for the XOR is called a hidden neuron. Because it's not an input and it's not an output. So it's hidden in the middle of the network. So that's another terminology that we need to keep track of. All right, so that's some basic perceptrons. The OR gate was a simple input-output network, and the XOR required a hidden neuron, and sometimes those are called multilayer perceptrons, and the OR network was just a single layer perceptron. All right, we're going to stop this lecture here. Next up, in the next lecture, is going to be, well, how do we learn the weights for a perceptron? Which means we're not just making up the network from scratch. We can actually use a strategy where we learn how to create networks that produce the outputs that we want.